Okay, so here we are. Today we're going to finish up the second half, or most of actually this lecture 16, which is about this large design example. It's the list processor example, and the reason I wanted to talk about this is that it kind of reinforces a lot of the concepts that we have been talking about up to this point, and it's a large enough example that it's not a trivial design, but it's not so big that we can't cover it in great detail. In fact, I'm going to go through a very detailed description of the design for you, and I think that should be helpful for you when you do your own designs. So last time, I think we did the preliminary uh, discussion about the design language, this register transfer language that I like to use. And we looked at an example of how we can use the language to specify a little bit of code and then use that code to determine what the proper data path and controller would be for a circuit that executes that code. So we're going to use the same idea with this list processor. And last time we introduced the problem specification, but let me repeat that now to remind you what we're looking at here. Okay, so our objective is to design a circuit that has the function of forming the sum of all the integers that are stored in a linked list. And we say the linked list is starting at location 0 in some memory block. And the linked list is formed as we normally do with a series or a set of nodes where each node points to another node, thus forming the list. So the first half of each node has a pointer or the address of the next node. And the second half of each node has an integer. That's the data. And our circuit should follow this linked list from the beginning to the end, adding up all those x values, the integer values. So for purposes of our little design here, we're going to assume all the pointers and the integers are 8 bits, just to keep things simple, and that the linked list is stored in memory. And this memory has an 8-bit address port and an 8-bit data port, as shown below down here. The pointer from the last element, the pointer in the last element of the list is a 0. That's how we know that we're at the end. Okay, that's the terminator or the null pointer. And we'll assume that there's at least one node in the list. So here's just kind of a block diagram showing the abstraction of our circuit. It's going to have a memory here, and then we're going to design this digital part here, which will have a clock signal, a start signal that resets the circuit to start at the head of the list, and then starts the process of cycling through the list. And then there's a done signal that we would like to use to signal when the computation is complete. And then the R signal here, which will be 8 bits wide, which is going to hold the final result. Okay, so how do we do this? Well, okay. Last time I think we talked about the component library. These are the set of blocks that were given, along with the delays. And these delays are sort of parameterized with n. And my claim is that these are somewhat realistic. They're very big numbers for today's technology, but you don't have to worry about the absolute numbers. The kind of relative numbers are what is important here. We say a half a nanosecond for simple logic gates. The register has a clock to queue time of 0.5 nanoseconds and a setup time of 0.5 nanoseconds. We say n-bit wide 2-to-1 multiplexer is 1 nanosecond. An adder is 2 log n plus 2. Next time we'll see how we can make adders whose delay is proportional to log of n, which is not the case for ripple adders where the delay is proportional to n. We're going to have a memory block which will have a 10 nanosecond read, and that'll be an asynchronous read. We're not going to worry about the write in this problem. We'll just assume that the linked list is already stored in the memory and some other circuit is doing the writing. And then a 0 compare block, which I claim would be something like this, 0.5 times log of n, log base 2 of n, because we'd have approximately, we would have log of n gate delays, and each gate delay is 0.5. Okay, so I think these are reasonable numbers. So we'll need those when we estimate the performance of our circuit. I want to review something about register clock enables. I think we've been using registers with clock enables all semester, and we talked about it functionally before. The idea is on the rising edge of the clock, if the clock enable signal is 0, that means the register will do nothing. It will not change its internal value. But if on the rising edge of the clock, if the clock enable signal is a 1, then the in value will be transferred into the register, and that will appear on the output after the clock to Q delay. Internally, really functionally, and it kind of looks like this. We could look at it, we could use a regular register that has no clock enable and a multiplexer here. And the output of the register feeds back into the one input of the 0 input to the multiplexer, and the in goes into the 1 input of the multiplexer. So you can see this has the desired behavior, because on the rising edge of the clock, if clock enable is 0, we just feed the value back into the register that it had previously, and it'll just not change. It'll retain its previous value. On the other hand, if the clock enable signal is 1 on the rising edge of the clock, then the in signal will be propagated through the multiplexer and will then be loaded into the register. Okay, so just keep that in mind when we're using clock enables on registers. Okay, the registers we're going to use for this example, just to keep things a little more interesting, we're not going to assume that they have a reset input. So we're going to have to reset those registers explicitly. And you'll see how I do that in a few minutes. Okay, so this part of the process, so we've specified the functional requirement that we want, and now we're going to think about the proper algorithm to achieve this function. Okay, in this case, it's really the procedure or the way the circuit will perform the action. In this case, the memory only has a single port. It only allows one access per cycle. So this algorithm is going to be limited to sequential execution, right? If in another case, if more input data was available at once, then a more parallel solution may be possible. In other words, if we could fetch or get more than one node of our linked list out of memory at the same time, we might be able to speed up the computation or have an algorithm that is more parallel. In this case, since the memory we have to only access one word of memory at a time, it's going to force kind of a sequential execution to this. But we'll do what we can given that constraint to make it as efficient and as high performance as possible. So the first thing is to kind of solve this problem, you need to think about what kind of state is necessary. That's usually the starting point for any design problem. And we already said we're going to have a memory that holds the linked list, but inside our list processor, we're going to need some state too. We're going to need a register, I'm calling it next, and a register called sum. The register next is going to we'll have the pointer to the current node that we're processing, because this linked list processor, or this list processor, is going to go through each node at a time, processing each node, and we have to keep track of where we are in the list. Right, so we'll have a register called next, and we'll also have a register called sum, which is going to hold the result of adding the nodes values up to this point, because the whole purpose is to add up all the x values, all the values of the integer part of the nodes. These are kind of like, if you're going to write a program, you'd think about the program variables that you need first, and then you would write the code. It's a similar thing here. You think about the state registers that you need first, and then we'll devise the action to change those state variables every clock cycle. Okay. Okay, so here I wrote in our little RT language a description of an algorithm that we could use to do the list processing. So first thing, remember the notation is semicolon here. Anything that happens before a semicolon, it happens all in one clock cycle. We can have multiple actions if multiple things happen in parallel, and those are separated by commas. So on the first clock cycle, we're going to do this. If the start signal is a 1, and then next will get 0, sum will get 0, and done will get 0. Okay, so we just initialize these two state registers and make sure this signal is a 0. Then we have a repeat loop, because we're going to repeat for one iteration of a loop for each node in our linked list. And the first cycle, we're going to add to the value in sum the previous value of sum plus the contents of the memory at next plus 1. Remember, next is a pointer to the node, so next plus 1 is the address of the integer value that's stored in the node. So we're going to index into memory using next plus 1. That'll give us a value, add it to sum, and put the result back in sum. That's the first cycle. And then on the second cycle, we're going to update the next pointer to be next gets the contents of memory indexed by next. Okay, that will just give us the pointer of the node that we're currently processing, and then will give us a way to point to the next node. This is similar. You may have written similar type code in C or C++ in order to follow a linked list. And we repeat this until next equals 0, because when next equals 0, then the computation is done. Okay. And then at the very end, R gets passed out through, or sum gets passed out through R, and done gets set to 1 to indicate that the computation is done. So this is a description in our register transfer language, and it becomes the basis for the data path and for a controller that can execute this computation. So I think if you look at this, you'd agree that this is kind of the most straightforward way that we could write this kind of program to achieve this function of adding up all the contents of the nodes. So we'll use this as a basis for a data path, and that's coming up next. Right. So we know in the data path we're going to have 2 registers, and then we'll need some other operators for here. For instance, there's an addition here, and there's an addition here, and there's an equal compare here. So we're going to need those blocks, and then it's just a matter of figuring out how to connect those together. Okay, so that's what I'm showing on this page. Okay, so here's our sum register. Here's the next register. Here's an adder that we're going to use to form next plus 1. Here's an adder over here that we're going to use for forming sum plus something, plus the new value, the x value coming out of memory. Right? And then here's the next, here's the equal comparator here. Where we can, we're going to have an output signal here called next underscore 0, and that'll be a 1 if the value we get from memory, the next value, which is going to come out of memory and through this comparator, is equal to 1. If it's equal to 0. If it's equal to 0, then this signal will be equal to 1. And that's going to go to the controller. Okay, so we can look at how everything is connected up here. According to this description, which is the RT register transfer language description. So the first thing is we look at the first clock cycle, and this first line here, if start is equal to 1, right, then what we're going to do is set next to 0 and sum to 0. So we're going to clear out these, initialize these registers. Right. So we're going to use it instead of reset signals. In this case, I'm going to use these multiplexers here, where one of the inputs to the multiplexer is a 0. So we have 1 for sum and 1 for next. Right. So what this means is the controller on this first clock cycle is going to set next select to be 0, and the 0 will pass in to next. On the rising edge of the clock, it'll clear that out. Likewise here, on the first cycle and this cycle here, the controller will set sum underscore select to 0, and that will pass a 0 and then clear out that register. On the other cycles, it's going to take the other input to the multiplexer. Okay, then we go into the loop. In the first cycle of each iteration, we're going to do sum get sum plus memory of next plus 1. Okay, so what we have to do to execute this is next plus 1, which will be on this node here, because this is just a combinational circuit here, this adder that adds 1 to next. It's going to go to this multiplexer, and we will arrange it so that A select is a 1, So next plus 1 will go into the memory as the address. The data will be the X value will come out, and it's going to go into this adder along with the previous value of sum, and then sum select will have been set to a 1 by the controller, and then the result will come back and go into sum. So that's how this statement gets executed. The reason we have this multiplexer here in front of the memory address is that sometimes we take next plus 1 and sometimes we take next. In fact, on the next clock cycle of the iteration, the second clock cycle of the iteration, what we want is memory of next. Next gets memory of next. So the way that works is here we use the top input of the multiplexer. Next goes into the memory. That will yield out of the memory the next value that comes down. It's going to go through this multiplexer because next select will be set to a 1, and then it'll get stored into that register there. Okay, so these two cycles get repeated using the data path as I've shown, but each time as next is coming out of the memory, as it's going in, getting set up to get loaded into that register, it also is getting checked here with this equal comparator. So the controller on this clock cycle, the second clock cycle, has access to that value, and it can decide to terminate the loop or to keep going. Right? So that decision will be made during the second clock cycle of the iteration loop. Okay, so I think I explained everything in the data path. Now the controller is a simple finite state machine, and it has 4 states. First state is that initialization state. It has 2 states that we're going to iterate through, these two, and then it has the final state when it's done, when things are done. Okay, so we're going to call the initialization state is called start. This state, the first one of the loop, is called compute sum, because that's what we're doing, and the next one is called get next, and then we have a done state here. Right. So you can see how the state machine works. If start is equal to 1, then it pushes us into this start state, and the control signals are set here. This is a more machine, so the control signals are sent according to the description I went through a minute ago. For instance, load sum equals 1. Load sum equals 1 is the clock enable on this sum register, which allows it to be changed on the rising edge of the clock, which will be at the end of this clock cycle. And then sum select will be 0, so we select the 0 here, so we can zero it out. Same thing here on load next and next select. And then done will be set to 0 because we're not done yet. Okay, so that'll be first state. And then when start is set to 0, that we assume the start is just goes for 1 clock cycle, and then this is going to transition over into this compute sum state, which will set the control signals appropriately. It's going to set this mux signal to choose next plus 1, right? So that's what we want. Here is next plus 1 into the memory, and then it's going to choose load, put load next to 0 because we don't want to change the next value on this clock cycle. We're going to change it on the other clock cycle, but we do want to change the sum signal, the sum value on this clock cycle. So we set that load signal to 1, right? And we set the sum select to 1, so we choose the output of this adder, and then done to 0, right? Okay, and then if start is still not 0, then we just unconditionally go over to next, get next. That's this state here. And what we want to do here is send the next value out as into the address of the memory, and then get a next value back and store it back into the register. Okay, so that's going to happen as shown here. A select gets 0. Load next is a 1 because we want to change the next register. Next select is a 1. We want to take that half. Then load sum gets 0, and done is 0. Right? And then we just go, and then as long as next 0 is equal to 0, that means that next value was not a 0, meaning we're not at the end of the computation, and start is not 0, we go back and repeat the compute sum. So that implements this loop here. So we just loop around here until next underscore 0 is a 1. That means we're at the final node, in which case we exit out into this done state. and then set load sum back to 0, and then set done to 1, or output a 1 for done. Right. So that's the way the thing works. Anybody want to ask any questions about that? It's kind of important that you understand this level, because we're going to go through some optimizations on this. But this is kind of the simplest implementation you could think of. Okay, so now next step would be to analyze the cost and the performance and the power. So the power we're going to skip for now. The cost, how would we measure it? Well, as we mentioned before, there's lots of ways we can measure cost. We're talking about not the NRE here, we're talking about the recurring costs. So this would typically be something like the number of transistors, or the number of logic gates, or the number of CLVs. It kind of depends on the technology. In this case, we're really just going to look at relative cost between two competing implementations. So we'll get into that in a little bit. Not worry too much about the absolute cost. The performance is important. So how do we judge the performance? Well, the performance in this case would be how much time total does it take to process a linked list of size n, let's say, right? So what do we know? Well, we know from our implementation that it's going to take 2 clock cycles for each node that we process, right? There's 1 clock cycle to get the X value, and then the 1 clock cycle to update the next pointer to point to the next node, right? So then the question, as far as what the performance is, or how long does it take to process a linked list, depends on what the minimum clock period is. It's going to be the minimum clock period times 2. That will be the total time to process a list, times 2 times n. So we need to figure out what the critical path is for this design, and then that will tell us what the maximum clock frequency can be. Right? Now, it could turn out the controller could be part of the critical path. We don't know that at this point. Right? So we've looked at the data path, but the controller I kind of left, as you can see here in this finite state machine, this abstract form. So in order to get an exact estimate of the critical path, we're going to have to look at the circuit for the controller. Now, as you know, there's different ways to design controllers. I did a design here just so we have something specific to analyze. And in this case, I chose to implement a one-hot finite state machine controller, because for me, it's kind of the simplest thing to do. So here's our state transition diagram here, and here's a one-hot finite state machine implementation for that. As you know about one-hot implementations, there's 1 flip-flop for each state here. So there's a start flip-flop, a compute sum flip-flop, a get next flip-flop, and a done flip-flop. Okay, and then this is the circuitry that gives us the transition from state to state according to our inputs, start and next 0. And then these are the outputs, which are the control points in our data path. We got the A select multiplexer, that's the address selector multiplier in front of the memory. We got sum select, turns out those take on the same value. There's the load signal for the 2 registers, sum and next. And then there's the multiplexer in front of each register select signal, the sum select and the next select, and then the done signal, which indicates that we're done. Okay, so you have to trust me. I'm not going to go through the detailed logic on this, but you can trust me that I have it correctly. So based on this, then we know what the controller input and output delay is. Right? So when we change to a new state, there will be a delay before the output signals are stabilized. It's going to be the clock to Q delay of the flip-flops plus any logic delay that's between the flip-flop and the output. Right? So for instance, this load sum signal, has 1 gate delay, which would be, in this example, will be 0.5 nanoseconds, plus the clock to Q delay, which I think is 0.5 nanoseconds from, or is it 0.1? We'll find it out in a minute from this flip-flop here, right? Also, there's going to be an input delay through, worst case, a couple of logic gates to get to into a new state. Okay, so we have that. So now we can do a detailed timing analysis, and that's what's shown on this slide here. There's a lot of information on this slide, so I'll go through it slowly. What I've done here is shown the analysis, showing the waveforms and the delays associated with the worst case path for each of the 2 clock cycles, or the 2 states associated with the body of this loop. Right? So the first one is the compute sum state, and the second one is the get next state. And I did an analysis of the path through this data path and the controller. So I'll show you how that works. Now, there's other paths, of course, exist for other paths exist for each cycle in the loop, but these 2 are the worst case ones for each iteration. Okay, so here's compute sum here. So we begin at the rising edge of the clock here. Okay, and then there's a clock to Q delay on the next register, right? Because that will have been changed. The cycle before was the get next cycle, so that register is changing there. So we'll see it actually change a little bit at the beginning of this compute sum state, or the clock cycle associated with the compute sum state. So that's this delay here. It's the 0.5 nanosecond clock to Q delay. Then this signal propagates along the wire. We're assuming 0 wire delay here. And then there's a delay through the adder here. Now, according to our specification before, an 8-bit adder, I believe it was 8 nanoseconds. Okay, so that's that. Okay, at that point, we have next plus 1 on this here, and that's, I didn't show the waveform for that, but then there's this signal. It's going to go through a multiplexer, and the multiplexer was 1 nanosecond, and then it goes into the memory, and the memory delay was 10 nanoseconds. It's here. Okay, that signal comes here. It's going into this adder here. A 15-bit add, it turns out, has, in this example, has a 10 nanosecond delay. Then there's 1 nanosecond for this multiplexer. And then we need 0.5 nanosecond setup time for the sum register. Right? Because at this point, the clock will go down here, and this is the clock's going to go up somewhere over here. So we need to guarantee a 0.5 nanosecond before the rising edge of the clock. So the soonest that clock edge would be right here at this point here. If you add all that up, that's 31 nanoseconds. So that's the kind of critical path for this compute sum. If we look at get next, which is this state here where we do next gets memory of next, here's the analysis of that one. So here's the rising edge of the clock. And then this would be a change in the controller. So here we have a 0.5 nanosecond delay to get the signal out of the controller, this A select signal. Right. And then that mux control, once the mux control signal is there, then we're going to have a 1 nanosecond delay for the next signal to go through the multiplexer here and then into the memory. And then again, this memory has 10 nanosecond delay, right? The value comes out, it goes through this mux, that's 1 nanosecond here. And then at the same time, it's going to go through the next 0 comparator here. And this was the one that's on the critical path here. That takes 1.5 nanoseconds. And you can see the next 0 signal changing here. And then there's a 1.5 nanosecond input delay into the controller, right? Because then it has to make a decision on which state to go to next. So we got that 1.5 nanoseconds here. Okay, so here's the kind of minimal period for this action here for the second clock cycle, and that's 15.5 nanoseconds. And you can see there's kind of an imbalance here. Okay, so that's the timing analysis for this implementation. And so here's kind of a summary of it. So the clock period T is has to be the max of the clock period for each state, because we can't have a different clock period for the two states. It's just the clock is repeating every time, right? So we have to take the worst case, which has to be greater than 31 nanoseconds. That was this top one, the compute sum state. So that means 1 over that means the frequency is going to be no greater than 32 megahertz. Okay. There's an observation here that we can make that this compute sum state does most of the work, right? Most of the components are inactive in get next. You think about it here, look, in compute sum, we're activating this adder, the memory, this adder, right? And then we put the result in sum. In the get next, all we're doing is activating the memory and putting the result back in the sum, right? So that's why we kind of have this imbalance here, is that there's more work being done in sum, in get sum. So you can see where we'd like to go with this. If we want to do some optimization, we're going to find a balance, find some way to kind of balance the work between those two states. So one thing we could do, since we have two adds in one and no add in the other, we could think about moving one of the adds into get next. Okay, so that's the strategy we're going to take for our first optimization. If we do that, we'll need less time for the compute sum state, and we should be able to raise the clock frequency. Okay, so we're going to get into some optimizations now. Okay, so the way we're going to do that, and this is kind of like pipelining, we're going to add more state register. In this case, we're going to name this register NUMA, which stands for address of number to add. All right, so we're going to update the code to reflect our change. No, we're still going to have 2 cycles per iteration, but we're going to change slightly what we do on each iteration. So if NUMA is a register, we assume it's going to hold a pointer not to a node, but to the X part of the node, the number to add part. Okay, that will change this first cycle of the iteration, this first state, to be something like this. It's going to be sum gets sum plus memory of NUMA, right? Instead of next plus 1, we kind of factored that plus 1 out and assume that NUMA is already next plus 1, right? It's the number to add. And then on the next cycle, what we can do is we can load from the memory at the location next, which was the next value, add 1 to it and put that into NUMA. So we can kind of pre-add to next and put that in NUMA. At the same time, we can deposit next into the new next value into the next register. Okay, and then once again, we just repeat that until next gets equal to 0. Right, so we've moved, kind of balanced the additions here. This cycle is going to have 1 addition, this cycle is going to have 1 addition. So let's see what that looks like in terms of the data path. So here's our new NUMA register. Right, so the initialization is similar to what we had previously, except now we also need to initialize NUMA to 1. Right, if next gets initialized to 0, that's a pointer to the first node in memory, then NUMA should point to the address 1. That's the location where the first X value will be stored. Okay, so then the way this works briefly is that on the first cycle, the compute sum cycle here, we get sum that gets fed back into the adder. At the same time, we take the value of NUMA, that goes into the memory through this multiplexer, which is makes the address of the memory. The data that comes out is the X value, and it comes over here and then gets added with sum. We put the result back into sum. And then on the next cycle, what we do is we go memory of next. So the next value gets sent to the memory as the address. What comes out is the new next value. That goes into this register here. At the same time, we send it down to this adder where we add 1 to it, and on the same clock edge as when we change next, we also change NUMA to be next plus 1. Right. So the incremental cost here for this is the addition of a register here and an extra multiplexer here so that we can initialize NUMA. Okay. Let's see what the impact is on the performance though. So here's the timing analysis with the new architecture, architecture number 2. I didn't put a copy of the data path here, so hopefully you kind of remember how it works at this point. So the compute sum now is somewhat compressed because we only have 1 add in there. So you can see here what happens is, again, we have some clock to Q delay for the NUMA register at the beginning of this clock cycle. Then we have the mux delay for the address mux to the memory. Here's the memory delay. Here's the 15-bit add delay. Here's the mux before the sum register, and then here's the setup time for the sum. So if you add all that up, that's 23 nanoseconds, right, which is down from what we had before. And then the get next state, it gets a little longer now. So we've taken some time from this clock cycle and put it in this clock cycle. So this is going to be 0.5 for the control signal A select, 1 nanosecond for the address mux for the memory. Here's the memory delay. Here's an 8-bit delay. Here's the mux delay for the NUMA register, and then the setup time for the NUMA register. Okay, so this is now our critical path. That's 21 nanoseconds. So we went from, if we go back to here, we had 31 and 15.5, and now we have 23 and 21. So they're much more balanced. So you'd expect this to be a more optimal design and higher performance, and it is. So new clock period now is 23 nanoseconds. So the frequency went up to 43 megahertz. Right. So you can ask yourself, there's a trade-off here. We had to add some extra cost. We had to add an extra register, in this case, an extra multiplexer. But we had a substantial improvement in the frequency. It went up from it's now at 43, and previously we had 32. Right? So went up something like 30%, and for a relatively small increase in cost. So I would say this is a pretty good trade-off. There's an interesting optimization we can do now that we've done this, is that you notice that the circuit only does 1 add per clock cycle. So in 1 clock cycle, we're using this adder to form the sum, and on this clock cycle, we're using this adder to form NUMA. Right? So you might ask yourself, well, why not share the adder for both cycles? Adders are relatively expensive. So maybe we can just have 1 adder and use the same one on each of the 2 cycles. Okay. So we can do that, and here's this optimization. This is architecture number 3. Got rid of the adder over here and moved the adder over here, and the NUMA register is over here now. So we had to add an add select multiplexer here to choose whether or not we just take sum and feed it back. Before, the sum value was hardwired into the left input to this adder. Now this adder needs, this input can be used for either feeding back sum or putting 1 in. The other input always comes from the memory, because it's either going to be next, to which we'll add 1, or it's going to be sum, x, to which we'll add the previous sum value. So we have to make this idea work, we need to add this multiplexer and the control signal for it here. But otherwise, we didn't have to add any other hardware, and we get to remove the 8-bit adder. Right. So the performance won't change. because this doesn't affect even though we had a multiplexer in here, it's not on the critical path. Critical path was dominated by the memory path, right? So the performance will be no change. The cost is small, relatively small, because a multiplexer is much less expensive than an adder. Therefore, you could say for sure this is definitely worth it. This is more Pareto optimal, this design. Right? Okay, so that was architecture number 3. Okay, so now we can actually do more optimizations. We can get this to have even higher performance. It gets a little more complicated, so I'm going to now introduce kind of a graphical aid to help us visualize the kind of pipelining and the timing of the circuit. So the aid is, these are called resource utilization charts. And just looking here to see if anybody, let's stop sharing for a second. I can't seem to look at the chat. Okay, there's no comments. Okay, so I'll just push ahead here. Okay, so resource utilization charts. Okay, so let me introduce the concept, and then we'll see how we're going to use it in this design. So hang on, I want to just check one thing. Yeah, okay. All right, so one way we can visualize these optimizations and possibly other optimizations is through this kind of chart here. These are used in high-level design to help us schedule operations on shared resources. Right? So the resources here, these are blocks of hardware or things that we can use in the design. For instance, a memory block gets used, and it might get used for different purposes at different points in time. And maybe a bus, which is a connection and a register file, ALU, for instance. Then so the resources are listed on the y-axis, and the time in cycles is on the x-axis here. So for instance, here, this is a different design. This is not our list processor, but imagine we could say the memory gets used to fetch A1 at this point in time, and then we transfer that value on the bus in this point in time. And at the same time, we could use the register file to read B1, and then we could use the ALU to add A1 and B1 together, or A1 and B1 together, right? And then we could repeat that process starting here, for instance. Okay. So it kind of shows us how we can overlap, kind of like a pipeline diagram that we used for processors, and helps us see how we can overlap operations. And for repeating operations, for iterative operations. Right? So in our example, there's 2 shared resources. There's the memory, and then there's the adder. Right? So we can, as shown here, we can show these charts to kind of analyze our 2 different designs. So the first unoptimized design, the one without the NUMA register, was shown here on the top, and the arrows kind of show the data dependencies. So on the first clock cycle, we do sum get sum plus memory of next plus 1. So you can see what happened here. We use adder 1 to compute next plus 1 in this cycle, and then that result gets fed to the memory. The memory fetches the x value. X value gets sent down to this adder 2, and then we compute sum there. Right? So we get to see the kind of the data dependencies within one clock cycle. Next clock cycle was next gets memory of next. So we use the memory here to fetch the next value, right? And the 2 adders were idle in that clock cycle, right? That kind of led to some of the inefficiencies. And then that repeats. Again, a 1, 2 for the next iteration. In the optimized solution, what we did is introduce that NUMA register. So you can see in that solution, what we did on clock cycle 1, sum gets sum plus memory of NUMA. So we used the memory on this clock cycle to fetch x, and then that value gets sent to the adder, and then we compute sum. And that happened all in one clock cycle. And then on the next clock cycle, we fetch next here, send that value over here, and we can compute NUMA with the adder, right, in the second half of this clock cycle, right? And then that repeats. Well, this data dependency here kind of means we have two things that happen in this clock cycle. There's the memory fetch and then the sum, and they're kind of in sequence with one another. Right? We can't really overlap those. That's why what this arrow designates. So therefore, we get kind of a long clock period here. Well, there's another way to do this, which becomes apparent when you look at these charts. If we had an X value, we could do something like this. On one clock cycle, we could fetch an X value and store it in a register. And the next clock cycle, we could use it, send it to this adder to form the sum. Right? At the same time that we're forming the sum here, we could fetch the next value out of the memory and put that in a register and put it over in the NUMA, and then put it into a register, next register, and then form NUMA the next clock cycle. Right? So we can kind of overlap all this stuff so that a single computation would kind of look like this. We fetch next, we form NUMA, and then somewhere down here there would be a fetch X based on that NUMA, and then somewhere over here there would be a sum based on that X. So we kind of spread the computation out in time, but we can overlap kind of maximally. And you can see these arrows now are going forward. We don't have any dependencies within the clock cycle. The results just go into a register, right? Kind of in a pipelined way. So if this works, then it would look as shown here. On cycle 1, we'd use NUMA to fetch X and put it into the X register. At the same time, we could use the next register, increment it by 1, and put that in the NUMA register. Right? So we do an add and a memory at the same time, but they're independent of one another. And then on the second cycle, we do an independent memory access and a sum. So we use the memory to get the next value. At the same time, you use an adder, or use the adder to add X to sum and put it in sum. And these two are unrelated. So we don't have a dependency within the clock cycle. The dependencies are spread out across clock cycles, and we can form that, we can allow that to happen by using extra registers. Yeah. Well, we already had the NUMA register, we'll add the X register. Okay, so if this works, then we get a very short clock period because the fetch and the add from each cycle would be independent. So the clock period would be the max of the memory time in the memory and the adder time instead of the sum of the memory time plus the adder time. All right. So that's kind of our final performance optimization here. So let's see if we can make that work. Oh, yeah, if we want to, I kind of alluded in the last slide how this would actually get scheduled, but we need to look at in full detail how a cycle would get scheduled. And so what we could do is just use the start and start laying out operations and see how it works out. So the first cycle here, and then we can overlap iterations. So we're going to lay out one iteration of the loop here. So here we compute, we fetch next, then here we form NUMA based on that next value. And then here we fetch X based on the NUMA value. And then here we compute sum based on that X value. Right? And then here could be another iteration like this. Right? You can see this is not a very efficient scheduling because we have all these holes in the chart. Right? So the adder is unused on this cycle, its memory is unused on that cycle, et cetera, et cetera. It's not really what we want. We want to be able to overlap iterations. Okay, so what we could do is just take this blue one and try to slide it into the white one here, right? So if we did that, we could overlap here, right? It's not a very good overlap because we're only overlapping the two iterations by one clock cycle. We could jump it over into here, right? So that's what I've shown here. So here's a white iteration, and here's a blue iteration, and then here's a yellow one, and then here's a red one. Now this is completely dense, so this is pretty efficient use of the data path, but it's kind of got this awkward thing that we have two next values, we have two NUMA values. Right? This next value doesn't, I guess maybe this would work, because when the next register would get reused by this one here, and then the NUMA, yeah, so this would work. It's not, it's a little more complicated for the controller, because basically what we have is two iterations, two nexts, two x's. That's not exactly the simplest thing we could come up with, but it would work correctly. There's actually a simpler way, and I'm going to show you. It's if you take this one iteration and you spread it out a little bit. Right, so we put an empty cycle in here, which sounds like the wrong thing intuitively, but if we do that, then the white iteration is here, and the blue one is there, and then the red one, yellow one is there, and so we get this really nice packing, so that we have two cycles of this kind of characteristic section here that represents the two cycles of the computation that we want, right? So we do an X and we do a NUMA in one clock cycle, and then we do a next and a sum on the next clock cycle. So these two, you can see now we have three different loop iterations active all at once, right? Which is the nature of pipelining. We have a short cycle time because there's no dependencies within the loop, and the full utilization, meaning only two cycles per result, and it changes the initialization a little bit because we have this time here when we need to initialize, and then we have a little bit of a time at the end. So what's going to happen is we have this special stuff we do here. Then we iterate this section, and I think it's n times or n minus 1 times, and then we have this little final finish up section. So the controller would have to have a few more states to handle this type of optimization. In fact, there would be two states to start. One would initialize next. It would clear the sum register. It would set NUMA to 1. It would clear X, and then it would get the next value. Right? And then we had two cycles here to finish up as shown in this chart. Okay, so now, let's see if I have it. Yeah, okay, so that's the highly optimized design here, so we can see what the data path for that looks like. I've added a X register here. There's a multiplexer here to initialize it when we need to initialize it. There's, turns out we need an adder mux here, adder mux select 2, because now this input into the adder, which used to come directly from the output of the memory, now has to come either from the output of the X register or from the output of the next register. And then there's some extra control signal for that. Right. So, but we can look at the performance now of this version. So it's going to be the max of time of the 4 different actions, right? So we've got this action, which is independent of that one on one clock cycle, and then we have this action, which is independent of that one on the next clock cycle. Well, it turns out, if you do the analysis, and I'm not going to show it here, that all 4 actions have the same time. They have 0.5 nanoseconds, which is the clock to Q, plus a mux delay, plus the big adder, plus a mux delay, plus a 0.5 nanosecond setup time. So they're all 13 nanoseconds. Each one is 13 nanoseconds. It's a very balanced design. This is probably the best you could do for this particular example. And so that's 13 nanoseconds. So the clock frequency then now is 77 megahertz. Which is nice. So there's other optimizations we could do, which are a little bit out of the spirit of what we're doing here. One would be node alignment restriction. So if the application of the list processor allowed us to restrict the placement of the nodes in memory so that they're all aligned at even multiples of 2, then the NUMA addition could be eliminated. Right? The controller could just set the low bit of the memory address. So it'd be set to 0 for getting next and be set to 1 for getting X. Right? So it's kind of a little tricky optimization we could do if the node locations were always aligned to 2 bytes. But they weren't, so we had to compute NUMA from next. If we could use a memory that's 16 bits wide, we could fetch the entire node in one cycle. Right? So something like this, we could fetch next and X all in one memory access, and then in the same cycle we could form sum, or on the next clock cycle we could form the sum. So that would allow us to do this processing with 1 clock cycle per node instead of 2. And that would cut the execution time in half. But again, to keep things interesting, I kind of forced it, so we needed 2 memory accesses per iteration. Okay, so here's some conclusions on this. So through some careful optimization, we increased the clock frequency from 32 megahertz to 77 megahertz. Right? So the 32 megahertz version was nice because it was very straightforward. It was easy to understand how it works. It kind of matched our tendency that we might have if we were going to write this as a program, right? But then we were able to add extra registers and kind of decouple operations on different clock cycles and kind of pipelined it that way. So we got it up to 77 megahertz, and this came at relatively little cost increase. In the end, it cost us, I think, 2 registers and 3 muxes. But we saved an adder along the way of doing that. Right? So the net cost increase was not very great. We use this kind of scheduling with resource allocation charts to help us figure out how to overlap and maximally use the resources. As I said, essentially through pipelining the operations, these extra registers, the NUMA register and the X register here, end up acting like the pipeline registers. So, question, something to think about here in the process that we went through. I asked the question, do you think a computer program could go from this RT language description to circuits automatically? Anybody want to say? Yeah. Is that not the point of RTL? Well, of RT, yeah, so somebody asked, is that not the point of RTL? So, well, when I say I put RTL here, I didn't really mean RTL, right? I meant register transfer language. So how about if I say this, could a computer program go from a C language description to circuits automatically? Maybe that's better. And because RTL, if you think of RTL as Verilog, that's the point of logic synthesis. But here we're specified this at a higher level. We specified it more like a program, right? So you could think of writing a C program that very much matches the code that I wrote for this list processor. And you know, we did these optimizations. I'm asking you to think about, do you think that some kind of compiler, hardware compiler, could do these optimizations? And of course, maybe not of course, but the answer is yes. There's something called high-level synthesis, which is different than logic synthesis. When we do logic synthesis, we start from behavioral descriptions in Verilog, which don't have these loops, right? Mainly is the big difference. Logic synthesis will go to logic gates, from some behavioral description and to LUTs. With high-level synthesis, we start with typically the C programs, and maps, figures out the data path and the control for these C programs, and maps it to hardware in a process very similar to what we did by hand. And they're pretty good, and they can do some optimization and loop unrolling and try to minimize the number of clock cycles per iteration of the loops and minimize the clock period of each cycle. And the tools are getting mature. They're starting to be used by real designers rather than Verilog in some applications. So you're going to hear a little bit about about high-level synthesis on Thursday, because we're going to have a guest lecture. My grad student, Jenny Huang, who's working on building hardware accelerators for neural networks. And she uses logic synthesis to synthesize her circuits. She's going to talk a little bit about that on Thursday after she talks about hardware architectures for neural networks. Okay, so I don't know if I had anything else. Okay, yeah, so that was the end of the list processing example. I'm going to go a little more into the scheduling. I'm going to check again in case somebody wants to ask questions. Okay, so you should take the time to look at the list processor example. All the details are there, so you should be able to understand everything that I did. And I think it's very instructive. Okay, so oops, I haven't. Okay, here it is. Okay, so I'm going to talk about something called modulo scheduling, and this kind of relates to what we were doing with the resource utilization charts before. And I'm going to first kind of review what we did with the list processor. We took one iteration in the loop, and we showed how it would lay out in time using the two resources. Our two resources in this example were the memory and the adder, and the memory gets used twice per iteration, and the adder gets used twice per iteration. Right? The memory gets used once to get the next pointer, and then once to get the x value, and the adder gets used once to compute NUMA and once to compute sum. And we had this little tricky thing we did where we spread out the iteration a little bit in time in order to make it better for overlapping other iterations on top of this one. All right, and how did we know to spread this out? Well, there's a technique for figuring this out. It's called modulo scheduling, and the goal of that is to find the schedule for one characteristic section of the computation. This bracketed piece here, this is the characteristic section of the computation. This is what repeats over and over again, right? N-1 times, I believe, in this case. So there's a little startup, which is kind of a degenerate versions of the characteristic section. Then there's the dense characteristic section part that repeats many times. And then there's this finishing part here. So the entire schedule can be derived by repeating the characteristic section and then repeating it with some pieces omitted for the starting and the ending part. Right, so what modulo scheduling does is for some computation on a set of resources, it gives us a way to find the optimal schedule of the characteristic section. Okay, so the way this procedure works is we first calculate the minimal length of the characteristic section. Right, this is going to be the maximum number of cycles that any one resource is used during one iteration of the computation, assuming that the resource can only be used once per cycle. Right. And then we're going to schedule one iteration of the computation on the characteristic section, wrapping around when necessary. Right. Each time the computation wraps around, we decrease the iteration subscript by 1. Right. And then if we do this and the iteration won't fit on the minimal length section, and it's not guaranteed to, then we can increase the section by 1 and try again. Okay. So this is kind of a greedy algorithm, but and it's not guaranteed to yield the optimal result, but it almost always does in my experience. Okay, so here's our example here. here's the computation chart here. This is an abstraction of the computation, right? So we get next, we form NUMA, we get X, and then we form sum, right? So this one uses the memory, this one uses the adder, this one uses the memory, this one uses the adder. Remember, we only have one of each now in our optimized design. So we want to figure out how to schedule this. So we know the minimal schedule length of a characteristic section is going to be 2, right? Because we need to use the memory twice per iteration. So we need 2 cycles for using the memory twice. And we're going to need the adder, use the adder twice per iteration, and we can only do 1 add per cycle. Therefore, we're going to need 2 cycles for doing the add. So that kind of sets the lower bound on the length of the characteristic section. So what we do then is take this computational chart or computational diagram and start scheduling it. So take the first get next I, next gets memory of next, put that in this time slot here. And then after that, we can compute NUMA based on that. This will go into a register. And then here's using the adder, compute NUMA. The next thing will be to fetch next out of the memory. That would go up here, but what we do is we wrap around. We'd like to put it in here. We can't put it in here because that slot is used, so we put it here. In the process of wrapping around, we went from I to sub I minus 1, which really what this means is it's going to be, the previous iteration is going to use this time slot. The next thing to do would be to form sum based on X, and that should appear here, but we're at the edge. So we kind of wrap around and we put it in this slot here. In the process of wrapping around, we make it I minus 2. All right, so this gives us a way to kind of schedule a computation or schedule this graph, 1 iteration, wrapping around, decreasing the subscript. So it shows us how the 3 different iterations are going to kind of coexist. And that becomes the section here, right? In this case, we let I equal 3. Here, I is equal to 4. Here, I is equal to 2, but there's no I equals 0, so that vanishes. Here, I is equal to 1, there's no 2, and there's no 0, so those 2 vanish. And likewise at the end. All right, okay, so that's modulo scheduling, and we could have used that here, but that would be the way you would probably do it if you're going to do this for real. I'll show you just another example so you can see this again. Here's another computation graph. Again, we're assuming this is repeating. This is a repeating calculation. This whole graph gets repeated every iteration of some loop. So we're going to assume that A, B, C, D, and E are stored in a dual port memory. It has two read ports, or 2 ports that can be either read or write, in this case. We're going to assume we have a single adder. So we can set that up this way. Going to have a resource chart that has 3 resources. The 2 ports of the memory. Each port can either be a read or a write, and then the adder. Right? Now, we know to do this, the characteristic section of a repeating schedule will be at least 3. Right? That's because the memory and the adder are used for 3 cycles during 1 iteration. Look, in 1 iteration here, we have to do 3 additions. There's only 1 adder, so we know we need 3 cycles at least to accomplish that. And then the memory is going to use, we can fetch 2 operands at once because it's dual port. We can fetch A and B or C and D, but we also need to store E back in, right? So we've got 3 different memory operations, so we need 3 cycles for that. So we're going to make a chart that has 3 columns in it, 3 clock cycles, and start laying this out. So here, first cycle, we can use memory port 1 for loading A and memory port B for loading, or memory port 2 for loading B. Then the next clock cycle, we can do this part, load C and D. And at the same time, since we have A and B in their registers, we can form their sum. So this add can take place here. and then this add takes place here. Now, the next thing to do would be to add the results of A plus B and along with the result of C plus D. So that would go here, but there's no place here, so we wrap around, and that addition forming E with the adder, this add right here takes place in here, and we decrease its subscript. In this case, I just changed its color to blue, and then the final operation is to store E in the memory, and the memory is busy here, so we put it over in here. Right. So you can see the blue iteration, how it ends up if we kind of spread this out, and the yellow one is like this, and then the characteristic section is this section here, and that just repeats. Okay. So it's a nice way to kind of achieve maximal packing by wrapping around and decreasing the subscript. So I think that's, yes, so that's the final slide in this lecture. So that's modulo scheduling, which is kind of, like I said, it was useful for doing the list processor example, and it's useful for other circuit designs as well whenever we have these kind of iterative computations with time multiplexed resources. So that is the end of lecture 16. Anybody want to say anything about that? I hope you found it useful and not too tedious. There's a lot of details there, but I think it's important to understand the details. So if you didn't quite get it, you might want to go over it at some point in the future. Okay, so I'm going to take the remaining 7 minutes and start digging into the next lecture so that we don't get too far behind. So let me share the next set of slides. Get rid of this one, and this is on adders. So we've been I've talked about previously the fact that we're going to look at adder circuits. We've studied the ripple adder here. You've looked at it in other classes, no doubt. And it's a nice circuit because it's easy to understand. It's very intuitive. It matches what we do when we use longhand addition, the kind of addition that we learned in grade school. Problem with it in hardware, it leads to a slow implementation because the ripple carry, right? So we're going to see what we can do about that. So we'll get into some adders that are a little less intuitive, but they're faster, and they're going to make a trade-off. In all cases, they're going to somehow use parallelism to the extent that we can, and do more than one thing at a time and increase the cost, but decrease the delay through the adder. Okay. And I like to look at adders partly because they're important circuits. They show up a lot. Computers, CPUs have multiple adders. They have adders in the ALU. They have adders in the for the program counter, perhaps. There's adders sprinkled out here and there, and they're used for various different things, for counters and that kind of stuff. So it's kind of important to know how to make the trade-offs between cost and performance. They've been very well studied over the years. I mean, there are people who spent their whole careers pretty much dedicated to coming up with fast adder circuits. Right? So it's a big field. We're not going to talk about all different adder architectures, but I'm going to show you a couple of my favorites, and in particular one called carry look-ahead adders, and those are the kind of adders that are in most CPUs, most processors these days. But we're going to start with some basic principles, and I'll get through that today, and then we'll continue this next time. So first thing, tricks with trees. We had a little of this the other day. This was the slide that I borrowed from Professor Demmel, who teaches our parallel computing course. And he talks about parallelism there a lot, and parallelism is quite important for hardware design as well. And we talked about the fact that we like trees when we do hardware design, when we do kind of reduction type operations, or really computing any function. If we can find a way to do it in a tree form, then the delay to that should be proportional to the log of the number of inputs. Right? And that's a really nice property to have, because if you look at adders, for instance, in a CPU these days, which are 64-bit wide CPUs, meaning the operands, the registers are 64 bits wide. If we had a adder that had a delay proportional to n instead of log n, we would have at least 64 gate delays and more actually for an add operation, and it wouldn't fit within one clock cycle, or we'd have to have a very slow clock. If we can make it a log, the log of 64 is 6, and so it's going to be a much smaller number. We're going to have a much higher clock frequency possible. So logs are nice, particularly if we scale up to bigger numbers. Logs get even much better than than n, obviously. All right, so we talked about different types of trees, and so when we talk about trees, we're really looking that are good for delay. We really are looking for kind of balanced trees, kind of as shown in the middle, because even though the top tree has the same number of nodes as the middle tree, the top tree has a delay proportional to n, whereas the balanced binary tree has a delay proportional to, or order, log n. But in order to make this work, the operators involved in the function that we're computing, or the reduction that we're computing, has to be, those operators have to be associative, so that we can regroup, to change the order that we're doing the doing the sub problems, right? There's another type of tree that's going to come up in the adders, and this is called parallel prefix or scan. It's related to a reduction, but it's a little more complicated, and let me show you why. So let's say if plus were associative operator, normal plus is, but let's say some operator we have, it's associative, and x0 through x sub p minus 1 are the input data, then a parallel prefix operation computes the following. It computes y sub j, which is equal to x sub 0 plus x sub 1 plus all the way to x sub j, for j from 0 to p minus 1. In other words, what we want to compute is x0. We want to compute x0 plus x1, and also x0 plus x plus 1 plus x2, plus x0 plus x1 plus x2 plus x3, all the way to the end. So what we want is we want to reduce these variables, but we want all the intermediate values as well, right? So not just the final. So tree reduction would just add all these values together, or plus all these values together. We want to do that. We want to get all the partial results also, as well, right? So we can do that with a special kind of tree shown here. There's different versions of this. This is a particular, where's my y? There's the y values. Here's a particular way of doing parallel prefix or scan operation. You can see how this works. So y0 is just x0. y1 is x0 plus x1. Y sub 2 is x0 plus x1 plus x2, right? And this kind of keeps going. Here we get x2 plus x3, and we add this to the sum of x0 plus x1, and that gives us x3. So it's this kind of funny structure, but if you look at it here, x or y sub 15 is the sum of everything. It's just everything kind of merges down here to the right and gets all added together and comes down. Right. So why am I showing you this? Well, I'm showing you this because we're going to use it for the adders, for fast adders. That's going to come next time. And I think we're out of time. So just keep this in mind. And next time we're going to use this parallel prefix for making fast adders. And so we'll do that next time. And I'll see you on Thursday. Any comments? Okay. We'll see you later. Bye-bye.